All right, hi folks, I'm recording a video for section 4.2, and this is related to graphing polynomial functions. I do have a graphing calculator available to me that I'm going to use to help demonstrate some of the problems. And in this section, you are going to need to use a graphing utility of some kind. You can either use a graphing calculator or you can use any online graphing utility. And there's many, if you just do a search, an internet search for graphing utilities, there'll be many such programs you can use, many free programs that do graphing. So even if you don't have a graphing calculator like this, don't worry about that. I'll give you one that I think is very easy to use. It's called, if you go to this website, www.desmos.com, this will be a very easy to use graphing program. So feel free to use that or any other graphing utility you might come across. All right, well, let's take a look at this question here. It says, analyze this function, and it's going to ask us some different questions about this. I'm going to revisit this. Let's use a different example here. Okay, let's do this one. All right. So the first thing it's asking me is, what is the end behavior of this graph? All right, well, let's talk about end behavior. What end behavior is asking you is, if you think about a graph, what's happening as x gets very large or very small? I'll give you an example of a few graphs that we can look at that we can analyze. So let me give you an example of, let's take the function y equal x squared. Okay, we'll do that one. And also let me draw the function y equal x to the third. All right, what end behavior is asking you about is, what happens all the way on the left side of the graph? What happens all the way on the right side of the graph? Notice on this top graph I drew for y equal x squared. Well, the graph is increasing on the left side and also increasing on the right side. If I go down to y equal x to the third, on the left side, the graph is decreasing, but on the right side, it's increasing. So we'd like to know what the end behavior of these graphs look like. All right, now notice they're asking us here, what does this graph behave like y equals what for large values of x? Really what that's asking you is, what is the leading term? Because when we want to study the graphical behavior, really the leading term dominates, and the leading term tells you how to visualize the shape of the graph. For example, if I had a function like y equals 7x squared plus 2x plus 9, and I wanted to know about the shape of this graph and the end behavior, really all I have to do is focus on this leading term. Same way, what if I had y equals 10x to the third plus 6x squared minus 2x? To figure out the end behavior, I'm really just going to look at the leading term. All right, well, you remember leading term, by the way, is the term that includes the highest exponent. Well, let me ask myself, what about the leading term of this? Now, I could multiply out this function to get expanded form, but I'm just going to imagine what happens if I did that. Well, if I multiply out x plus 7 squared, I'm going to end up with an x squared term. And then if I was to multiply that by this negative x back here, I would end up with a negative x to the third as the leading term. All right, so for this example, this is going to behave like negative x to the third. So the way I'm coming up with that is I'm really just coming up with the leading term. And if you want, you could just multiply this function out. I took a little shortcut, and I didn't have to multiply that. All right, what about the x-intercepts? Well, for the x-intercepts, that's where you let y equals 0. So for the x-intercepts, I'm going to let y equal 0. All right, well, if I do that, I'm going to end up with 0 equals x plus 7 squared times 3 minus x. But anytime I have a quantity multiplying equal to 0, I can separately set each parenthesis equal to 0. So I'm going to set x plus 7 equal to 0. You know, really, if I think about setting x plus 7 squared equal to 0, the only way this quantity could be 0 is if the quantity inside the parentheses is 0. And I'm also going to take 3 minus x and set that equal to 0. Well, for this first one, I'm going to subtract 7 from both sides, so that means x equals -7. And over here, I'm going to add x to both sides of this equation because I want to get x by itself. So that's going to give me x equals 3. So I have two x-intercepts, x equals -7 and x equals 3. So I'll enter those answers, -7, 3. All right, now they want the y-intercept. Well, you remember, anytime you want to know an intercept, you let the other letter equal 0. So for the y-intercept, I'm going to let x equal 0. So let me go back to the original function, and I'm going to replace x with 0. So that's going to be y equals 0 plus 7 squared times 3 minus 0. Well, that's just going to be 7 squared times 3. And of course, that's 7 squared is 49. 49 times 3 gives me 147. So it looks like the y-intercept is a pretty big number. It's going to be 147. So I'll enter the answer here. The y-intercept we calculated as 147. All right, let's see if there's a few other questions here. What are the zeros of this function? Well, actually, if I think back, zeros and x-intercepts are one and the same. Remember, a 0 is really an x value where the y is 0. But that's exactly what we figured out back here when we were figuring out x-intercepts. We set the y value equal to 0. So the answer here is going to be exactly the same as the x-intercept answer. So x-intercepts and zeros are really the same thing. So I'm going to enter -7, 3 for that. All right, so now they're asking me about multiplicity. Remember, multiplicity is based on the exponent that shows up in the factored form. So if I come back to this original function, I'm going to come back here to this original function, and I'm noticing for this original function, this first parenthesis has a multiplicity of 2 because the exponent is 2. So this was the 0 of -7, but it's going to have a multiplicity of 2. This other function here was a 0 of 3, but I could think of it as having exponent 1, so that's going to be multiplicity of 1. Now, you also might remember that when we were talking about x-intercepts, let me draw a little graph here. And here is the x-intercept of -7. And here is the x-intercept of 3. If the multiplicity is an odd number, like a multiplicity 1, that tells you the graph just crosses through the x-axis. So I know here for this x-intercept, the graph just crosses through. When it's multiplicity 2, if the multiplicity is an even number, that says the graph touches the x-axis and turn around. So maybe this graph does something like this. It comes up, touches, doesn't go through the x-axis, instead it turns around. All right, so now let's go answer this question. It says the lesser 0. Well, in our example, the smaller 0 is the -7 number. And that had a multiplicity of 2. So in this box, I'm going to enter multiplicity 2. When you have an even multiplicity, it means the graph just touches the x-axis. And the 0 was at x equal -7. All right, let's go to the greater 0. The greater 0 was the 0 of 3. Well, that had a multiplicity of 1. And if the multiplicity of 1 is 1, that means the graph crosses through the x-axis at x equal 3. All right, what's the maximum number of turning points? So you might remember that for the maximum number of turning points, this is always 1 less than the degree. So 1 less than the degree. Well, you might remember that the degree here was degree 3. Remember we said here the leading term for this example, we figured out was -x to the 3. So that's degree 3. That means the maximum number of turning points is 1 less. So that means the maximum number is 2. Finally, they want us to draw the graph. All right, well, let me come back up to our graphs here for a second. And here's what we can conclude about the shape of the graphs when we know the leading term. If the leading term, let me write some examples here. I'm going to make this be y equals 7x squared, let's say. And I'm going to make this y equals 5x to the 3rd. Okay? Now, if the degree is even, so here's an even degree, and if the leading coefficient is a positive number, 7 here is a positive number, then the graph is going to look like this parabola that opens up. Now, this graph would have the same shape if this happened to be y equals 7x to the 4. It would be the same shape if the function was y equals 7x to the 6. Okay, so anytime the degree is even and the leading coefficient is a positive number, the graph is going to look like this shape that you see here. I'm going to call this graph A just to label it. All right, let me come down to the bottom graph. I'm going to call this graph B. Anytime the degree is odd, notice here 3 is an odd number, and the leading coefficient is positive, like this number 5, the graph is going to look like the shape I have here on this diagram. It's going to start down and end up increasing like this. So even if this graph was y equals 5x to the 5, it would still have the same general shape. Even if it was y equal 11x to the 7, it would have the same general shape. All right? But what if I make the leading term be negative? Let me come over here. What if I made the graph be y equal -7x squared? Well, you might remember when you put a negative in front of a function, it transforms the graph by reflecting it across the x-axis. So -7x squared is going to take the graph and flip it upside down like this. And again, it would be the same thing if this graph happened to be y equals -4x to the 6, let's say. It would have the same general shape. So if you have an even degree and the coefficient is a negative number, it's going to follow this pattern like I'm drawing here in graph C. Let me do one more. What if I take 5x to the 3rd, but I make it a negative? So now I'm going to make this y equal -5x to the 3rd. Well, again, if I put a negative number in front, remember it's going to reflect the graph on the other side of the x-axis. So whatever was below the x-axis flips to the above, and whatever was above flips to be below. So now this graph is going to end up looking like this graph. I'll call it graph D. So even if this was y equals negative 9 x to the 5, it would still have the same general shape. All right, so by looking at the degree and looking at whether the leading coefficient is a positive or a negative number, you can classify the shape as either A, B, C, or D. Well, let's go to our example. Our example was the leading term was negative x to the third. Well, that has an odd degree, and the leading coefficient is negative 1. So that's going to match up to our graph D. So the shape of our graph has to be similar to graph D. Well, that means this answer here, answer B, is out of the question. It doesn't match up to our shape of graph D. The same thing for our answer D, doesn't match up to the general shape. So my answer is either going to be choice A or choice C. Well, the other thing I could do is use x-intercepts. Remember, our x-intercepts were negative 7 and 3. Well, if I look at this choice C, it doesn't have an x-intercept back here at negative 7. So I know choice C is not correct. If I look here, here's an x-intercept at negative 7. Here's another x-intercept at 3. So it looks like choice A is the correct choice for this one. So I'll go ahead and select choice A, and that should do it. All right, let's do maybe one more like this. Let me clear the screen. Okay. By the way, I meant to, let me go back for a second. I meant to graph that previous example. Let me go back to this example we did. And I want to show you how you could graph it on the graphing calculator. So let me come over here, and I want to graph this function. All right, well, anytime you want to graph, first thing you have to do is enter the function in the calculator. To do that, you come over here to this y equals. So I'm going to click the y equals. And now it's ready for me to type in the function. Remember, f of x is the same as y. So really, I can think of this as like a y equals. All right, now I'm just going to type this part of the function into the calculator. Now, anytime you want to type in the letter x, you can hit this button right here. So this is the x button. All right, so I'm going to put a parenthesis. I'm hitting this button right here to enter an x. X plus 7. Close the parentheses. And I want to enter an exponent 2. I can use this button right here to put an exponent 2. Now I need another parenthesis for 3 minus x. Close parentheses. All right, so I use this y equal button to enter the function. Now if I want to see a graph, I'm going to come over here to hit the graph button. And it's a little hard to see, but I'm going to zoom out. So let me zoom out. Now one way you could do this is go to zoom, and you could select the zoom out function. But another way to do this is to use a little bit of a shortcut, and I'm using the arrow button here to scroll down. There's an option that's called zoom fit. And zoom fit is where the calculator does its best to show the important characteristics of the function on the window. So I'm going to try that. I'm going to hit enter for zoom fit. And what the calculator tried to do is to show the x-intercepts here. So it's a little hard to see, but here's the x-intercept of negative 7. Here's the x-intercept of negative 3. Okay. Let me go back. I'm going to go to z-standard, number 6. Z-standard is getting just a standard viewing window where the x and y axis go from negative 10 to positive 10. All right. But maybe I want to zoom out on this a little bit. So I'm going to go to zoom, and I'm going to go down to option 3, which is zoom out. Hit enter. Now, if I hit enter again, the graph is zooming out. I'm going to hit enter one more time, and the graph will zoom out once more. Okay. Now, you can actually go in and adjust the window yourself manually. So how about if I want to make the window match the window in the graph? So I just click the button window. If I come here to my graph, I'm noticing that the x-axis is going from -20 to +20. So I'm going to make the min and max on the x-axis match that. So I'm going to make this -20 and +20. How about the y-axis? It looks like the y-axis is going from a min of -300 to +300. So let me adjust that. I'm going to make this -300 to +300. I just want to be able to match the graphs that my math lab is giving me to make it easy to determine the correct choice. And I'm going to hit graph now. And now the graph clearly matches choice A and none of the other choices. Okay. All right, well, let's go to the next example here. And let's graph this one on the graphing calculator just to give us kind of a head start as to what we might expect. So I'm going to come here again to y equals. And let me change this. I'm going to delete. I can hit clear here. I just hit the clear button to kind of wipe out the previous example. Let me type in our function. It's -2 parenthesis x plus 2. And I need another parenthesis that's x. Remember, I hit this button right here for an x. X subtract 3, close the parenthesis, and now I need an exponent 3. Well, this button here, this up arrow, is the way to enter an exponent. So I'm going to hit that button and put a 3, and notice I have an exponent 3. All right, let me go ahead and click graph. Let's see if we can get a sense of what's going on here. So I could see this graph. I might want to zoom out. Let's try zooming out 1, just to get a little better view. All right, well, that I meant to say zoom in. I'm sorry. Let me do zoom in. I meant to do zoom in, not zoom out. And I'm going to zoom in one more time. By hitting enter again, it zooms in. All right, well, that gives me a pretty good idea of what the graph looks like. Again, I could go into window and set up the window to match what my math lab shows. So maybe we can come back and do that in just a minute. All right, well, let me go to part A. What's the end behavior of this graph? Okay. First, I'm going to make up a little table here to help out, so that we can know that by looking at the degree and looking at the leading coefficient, what does the shape of the graph look like? Okay. All right, let me make up a little table here. And also, let me do maybe I'll do a little example of a function, and then we can see what the graph looks like. All right, let's say it's degree even degree, and the leading coefficient is positive, let's say. So an example of that might be, let's say y equals 4x to the 6. Well, this graph is going to look something like this. Okay. All right, let's do another line in the table. What if the degree is even, but now the leading coefficient is negative? An example of that, how about y equals -11x to the 4? Well, this graph is going to have a shape that opens down. Remember, this would flip the original graph across the x-axis. So maybe this will look something like this. Remember, the important part of this is the end behavior. What happens at the ends of the graph? Is the graph going up, going down? That's what these graphs are intended to show. All right, well, let me flip it now. How about if the degree is odd? And what if the leading coefficient is positive? So an example of this might be, let's say, y equals 12x to the 5. So the coefficient is positive, but the degree here is degree 5. That's odd. Well, this graph is going to go something like this. And one last entry in this table, What if the degree is odd, but now the leading coefficient is negative? So this might be an example like y equals negative 7x to the third. Well, that's going to take the graph I just drew and flip it upside down. When I say that, I mean reflect across the x-axis. So this graph will do something like this. All right, so this will be a guide that will give us a sense of what's happening with this graph. By the way, when I look at my graphing calculator, the graphing calculator is showing me a graph that looks something like this. It's kind of going up and then coming down and going like this. So this is what the graphing calculator is showing me. But that matches up to line number 2 in my table. So as we do our analysis, we're gonna see that this is function they're giving us is even degree, and the leading coefficient is going to be negative. All right, well, let's work it out. So what I want to know here is, what is the leading term going to look like? Because remember, the leading term tells me about the end behavior of the graph. Well, I could see the leading coefficient is going to be a negative 2 in front. So it's going to be a negative 2. And what's the degree? I'm really asking, what's the highest exponent? Well, this parenthesis in the back is going to generate an x to the third. And then this first parenthesis is going to give me an x. So if I was to multiply these together, it looks like it's going to get me an x to the fourth. So the leading term here is negative 2x to the fourth. And yes, it is an even degree because it's degree 4. It is a negative leading coefficient. Our leading coefficient is negative 2. So the answer to part A here is enter the leading term. So it's negative 2x to the 4. All right, let's keep going. Now they want us to figure out what are the x and y intercepts. All right, let's start out with the x-intercepts. Well, for the x-intercepts, we're going to set y equal to 0. Okay, well, with y equal to 0, I'm going to end up with 0 equals negative 2, x plus 2, x minus 3 to the third. But then I set each one of these parentheses separately equal to 0. Okay? Well, if I set that first parenthesis of x plus 2 equal to 0, right, so this parenthesis is going to get me x plus 2 equals 0. Of course, I'll subtract 2 from both sides, so it looks like x equal negative 2 is one x-intercept. And the other parenthesis is x minus 3 squared. But the only way x minus 3 squared would be equal to 0 is if the quantity inside x minus 3 was equal to 0. So that's going to get me another x-intercept of x equal 3. All right, so those are the two x-intercepts. Let's go ahead and enter those. So the x-intercepts here are negative 2, 3. All right, now it wants to know what's the y-intercept. Well, for the y-intercept, I let x equal 0. Remember, you always let the other letter equal 0. So I'm going to let x equal 0 in that original function. All right, so that's going to be negative 2 times 0 plus 2, and then 0 subtract 3 to the third. All right, I'm going to work this out. This is going to be negative 2 times 2 times negative 3 to the third. Okay, but negative 3 to the third is negative 27. So this is going to be negative 2 times 2 times negative 27. And you can work this out on your calculator. Notice this is going to turn out to be a positive answer. And I think if we work this out, this turns out to be 108. So it looks like the y-intercept here is 108. I'll enter that here, 108. Okay. What about the zeros of the function? Well, keep in mind the zeros are the same, exactly the same as the x-intercepts. So because we said the x-intercepts are -2, 3, the zeros are going to be exactly the same. So -2, 3 for the zeros. And remember, the zeros are asking you what x values have the y value equal to 0. And of course, that's exactly the way you find the x-intercepts. You let y equal 0. All right, now they're asking me about multiplicity. Well, when I go back and look at this original function, I'm seeing the 0 here of -2 has a multiplicity of 1. And then in the back here, this 0 of 3 has a multiplicity of 3. Remember, you're really looking at the exponents to identify the multiplicity. All right, so now it wants me to start out with the lesser 0. Well, our lesser 0 was this number -2. And -2 had a multiplicity of 1 here. Okay, so that first has a multiplicity of 1. And you remember, if the multiplicity is odd, that tells you the graph crosses the x-axis. And this was at a 0 of -2. The greater 0 here was our 0 that x equaled 3. Well, that had a multiplicity of 3. Now, if it's an odd multiplicity like 3, the graph does still cross the x-axis. I would only be entering the answer touches the x-axis here if the multiplicity was an even number. All right, and this 0 was a 0 of 3. All right, what's the maximum number of turning points? Well, remember, the maximum number of turning points is 1 less, 1 lower than the degree. Our degree was degree 4. So that means the maximum number of turning points is 1 less than 4, which is 3. All right, last item is they want me to select the correct graph here. All right, well, let me do this without the calculator, then I'll use the graphing calculator. So let me do it first without the graphing calculator. Because our leading term was -2x to the 4th, I know that polynomial functions that have an even degree but a negative leading coefficient have to have this end behavior where the graph is going to be decreasing on both the left and right side. Well, graph A and B show that kind of behavior. Graph C and D are increasing on both sides. No good. So graphs choices C and D are out of the question. So I'm going to cross out C and cross out D. The other thing that I can use to help me out here is using the x-intercepts. So the x-intercepts here are going to be -2 and +3. And if you notice, this might be a little hard to see, but if you notice here, each one, because this scale goes to 10, each one of these tick marks is 2. So if I go to graph A here, you might notice they're showing me an x-intercept of 2. Now what I can do is I can press this zoom in button. Let me do that because this is a little hard to see. So I'm going to zoom in a little bit. Actually, I can go like that. And let me try to move this down here. Can you see this x-intercept is clearly at 2 for this graph? But we didn't have an x-intercept at 2. We had an x-intercept at 3. So this graph is no good. So choice A doesn't have the correct x-intercept. Let me zoom in on graph B. Let me take a look here at graph B. Can you see right here, graph B does have an x-intercept at 3 and another x-intercept back here at -2. So clearly this graph is the correct answer. It has the right end behavior and it has the correct x-intercepts. So it looks like answer B is the correct answer. Let me go back to the calculator and let's just double check on the calculator. So I already entered the function here in the y equals button. But let me go to the window button because I want to set up my viewing window to match the My MATLAB scales on the X and Y axis. I'm going to go to Window. And the X-axis here on this graph is -10 to +10. So I'm going to make this -10 to +10 for the X-axis. And it looks like the Y-axis is going from -500 to +500 in the MyMathLab graph. So I'm going to match that. Hit graph now. And I can see that the only answer that makes sense now, according to MyMathLab, is it's matching choice B. I can see it doesn't match choice A. So using the graphing calculator gives me confidence that my answer of choice B here was correct. All right, let me look at one more example because I want to show you a question that does require either a graphing calculator or a similar type of utility. All right, so what this says is use a graphing utility to find the quadratic function of best fit for this data. All right, well, here's what they're asking us to do. Imagine I was to draw these XY points on a graph. So let me draw these XY points on a graph, okay? And let me do this just to kind of quickly graph this. I'm seeing the X values go from about 25 to 75. So I'm going to make this horizontal go from 75, 50, 25. I'm just doing a quick graph here because I want to get a sense of what this graph might look like. The vertical scale is going to about 500, let's say. So I'm going to make this 500, 400, 300, 200, 100. Okay, let me graph these points just in a rough kind of way. The first point is 25, 66. So I'm going to come over to 25 and go up to about 66. And I'm just going to try to roughly eyeball these points. All right, next is 35, 110. So 35, 110 might be here. 45, 167. 45, 167 might be here. 55, 247. 55, 247 might be here. 65, 339 might be up here somewhere. And then 75, 450 would be up here somewhere. So what this is asking us to do is imagine you have some points. We'd like to be able to come up with a quadratic function that best matches the points. Okay, so let me give you maybe another example. How about if I was to graph some points that did maybe something like this? Here are some points. And I want to come up with a quadratic function that matches these. Well, I'd be trying to come up with a parabola, right? A quadratic function that might look something like this. It's not going to go through each point exactly because these points are not exactly on a parabola. But we call it best fit. It means I want the parabola that comes closest to those points. All right, well, this is where the graphing calculator comes in. There's a program or a function called quadratic regression. And what quadratic regression is going to do is allow you to come up with the quadratic equation that best fits these points. So we're going to let the calculator come up with the equation of this red parabola here. All right, so let's go do it. The first thing we have to do is enter the data into the calculator. So step one is going to be to go to stat edit. Stat edit, by the way, the reason this is stat is this is somewhat of a statistical technique. This idea of doing what's called regression analysis is a statistical technique. So we're going to go to stat edit. Edit's going to let us input the data. And when we do that, the calculator is going to show us two lists. It's called list one and list two. And we're going to enter this data in these two columns. All right, so let me do that. I'm going to go to stat edit. I'm just going to hit enter here. And notice here's list one and list two. All right, I'm going to go ahead and enter in the numbers. So I have a 25 as the first X value. 35 as the next x value. 45, 55, 65, 75. All right, now I want to enter the corresponding y values in this list too. So I'm going to use these arrow buttons to go back up and go to the top of list 2. Now I'm going to enter the y numbers in. So I have 66 is the first y value, then 110, then 167, then 247, 339, and 450. Okay, got it. All right. I'm just going to double check that I typed in all these numbers correctly. Looks good. All right, now I've entered the data. Let me go to step 2. Step 2 says go to stat calc, because now we want to do some calculations. And I'm going to select an option that says quadratic regression. And when I do that, the calculator is going to give me the best fit equation that comes closest to the data points. Okay, so let me come over here. I'm going to go to stat. I'm going to use the arrow to move over to calc. And if I come down here, you might notice line 5 says quadratic regression. So I'm going to come down to line 5, hit enter. And it's telling me that the X data is in list 1, the Y data is in list 2. So that's all correct. So now I'm just going to scroll down and hit calculate. Okay, and so here is the equation. It's telling me that the quadratic model or the quadratic equation is y equals ax squared plus bx plus c. Well, that sounds familiar because that's the standard form of a quadratic equation. But now it's going to give me the numbers to plug in for a, b, and c. Okay, so you can see here's the number for a, here's the number for b, here's the number c. In this example, it's telling me to round to 3 decimal places. So for a, I'm going to round that to 0.085 x squared, rounded to 3 decimal places. The b number is negative. So actually, I guess I'll make this a subtraction sign here because the coefficient is a negative number. So I'm going to write this as minus 0.805x. And I'm looking here for the C number, and the C number looks like 33.290. Again, rounding these results to 3 decimal places. Okay, and that's the answer that I would type here in the answer box. And this graph is the best fit to these data points. All right, folks, hope this is helpful as you're working in section 4.2 on graphing these various functions.